Okay, so we are creating models for real life situations by modeling how these given quantities are changing at given times, right? So that was the first thing that we did. We worked quite a bit on that. Then we had some work on the COVID model. And that was just to get an idea of why we care about differential equations. The second thing that we did is, oops. All right. So the second thing that we did is we started talking about what a solution to a differential equation is. Right? So we said, what are solutions of differential equations? And so we said, if we have just a differential equation and we look for the solution, the general solution that satisfies just that differential equation, then we're going to get a general solution. Right? But then we said, okay, if in addition to the differential equation, you're actually given an initial condition as well. So if you're given a differential equation and an initial condition, which is the same as being given an initial value problem, then you have a particular solution, which means the solution that has that specific derivative, but also that satisfies a given initial condition. Right? So, and we said, okay, well, if we want to verify if something is a solution, we just have to plug in that function into whatever equation. Now, last week I gave a practice set number 10, and for the weekend, I said you should be able to do problems 1 through 4. Is there any questions about problems 1 through 4 that you would like? And I see a show of hands for those of you who tried at least problems in number 1. That's good, that's good. Some problems in number 1. Although I only see about 11 hands, okay, 12 hands. That's not ideal. I will emphasize, at this point, I can't check whether you're actually working on your homework. So you need to make sure that you do that on your own. All right, so that's for problem number 1. Did anybody try at least problem number 2? Okay, problem number 2. In problem number 2, there was a typo. I posted the 3 typos that there are that I found so far in the problems. I don't think there's any more. But make sure that if at some point you get confused, you verify that the problems that you found are not in problems. I think there's a typo in 2A, a problem in 3C, and a problem in 4B. Okay, so there's typos in those problems. Make sure that you go back and you correct based on what I posted yesterday. All right, so there's no questions. Everybody is okay with this? No. Mm-hmm. All right, maybe I'll do one of them. Yeah, I'll do one of them and we'll see how this relates to what we did last time. So we have an example. And I'm going to do a problem in 4. So I'm going to do problem 4B because that collects everything that we had in class. Okay, so what the problem asks us to do is to verify that y is a general solution of the differential equation that you're given, and to find the particular solution that satisfies the initial condition. Right, so that means you're going to have a differential equation. You're going to have an initial condition, and you're going to have a function that satisfies the differential equation. What we're trying to find is a function that also satisfies the initial condition. Right? So differential equation in this case, so the differential equation is the equation that satisfies, is the equation that is satisfied by the function. So in this case, that is y prime minus 2y minus 4x is equal to 0, right? Then the initial condition is going to be y of 1 is equal to 4. Right? And so together, if you have a differential equation and an initial condition, what you have is an initial value problem. All right, so this is what we have so far. Now, the problem is giving you a possible function. Y is equal to c times e to the 2x minus 2x minus 1. Right? And what the problem is asking you to do is to verify that y is a general solution of the differential equation. So you want to verify that this is a general solution of the differential equation. And then you want to make sure that you find the specific solution that will actually solve the initial condition, right? So the first thing is to verify that this type of function verifies this type of equation, and then you're going to find the one solution that actually satisfies this initial condition. Now, before I get started on this, can anybody explain to me why this function is not unique, why this corresponds to a family of functions?
Because the c still has not a specific value yet.
Yes, exactly. So we have a constant over here that's c, for which we don't know the value yet, right? So c over here is a constant, but we don't know what its value is yet. So that means that depending on the value that that constant c has, the function that we're going to have is different, right? So for example, if we have that c is equal to 2, my function would be 2e to the 2x minus 1. And that function is not the same as the function y is equal to negative 3e to the 2x minus 1. So depending on the value that I have, the function that I'm going to get is different. Now, what I'm trying to get first is to check that this is the general solution. So this type of function is going to be a solution of my differential equation. Okay, so how do I do that? I verify the left-hand side, and I make sure that that's going to give me the same right-hand side as the one that I have in this differential equation. Do I have any questions so far? Okay. So I have the left-hand side, which is y prime minus 2y minus 4x. And what I'm going to do now to verify that my function y is a solution of this equation is to plug in y over here into each one of the instances of y that I have, right? So that means if y prime, if I have y prime as the first term here, then I need to have y, which is this whole thing, prime as the first term. So I'll have that this is c times e to the 2x minus 2x minus 1 prime. Okay, so that's the first term. This is just y prime. Then I have minus 2 times y, so minus 2 times c e to the 2x minus 2x minus 1. And then I still have minus 4x. Of course, I don't have to replace x because what I'm trying to do now is just replace the values of the constant to see if they correspond. So essentially, I've replaced y prime over here with this term, and I've replaced this y over here with the function over here. Okay. Then, if I want to verify the function, the solution, I do still need to verify that once I apply this operation to my function over here, the equation is still going to be satisfied. So I'm going to have the derivative of c times e to the 2x. So that's c, and the derivative of e to the 2x is going to be e to the 2x times the derivative of the inside, which is 2 in this case. And then minus 2 and minus 0. But minus 0 is like doing nothing at all. So I can just leave this as 2c e to the 2x minus 2. And then I'm going to distribute the 2 here onto the second term because I know that eventually I would like to simplify everything. So that's what I'm going to try to do. Then I have minus 2c e to the 2x minus 2 times minus 2x, so that's plus 4x. And then minus 2 times minus 1 is plus 2. And then this is minus 4 times x. Okay. And at this point, we're already getting to where we want to be because we know that now 2c e to the 2x is going to be canceled with 2c e to the 2x over here. We're also going to get that negative 2 plus 2 is equal to 0. And we have that 4x minus 4x is equal to 0 as well. So that means that this whole thing is equal to 0, which is exactly what I want, right? Because this is my right-hand side. Okay, so this means is that I have that my left-hand side, once I replace by this function, is equal to the right-hand side of the equation. And so I have that y equals to c e to the 2x minus 2x minus 1 is a general solution of y prime minus 2y minus 4x is equal to 0. Can I see a show of hands for those of you who understand what I'm doing over here? Okay, good. I have 15 out of 16. Oh, 16 out of 16 hands up. That's great. So everybody understands what I did over here. I'm just verifying that this is a solution, right? So it's the same as if you had like an equation in terms of x and you were just trying to plug in the number that you already found to be a solution. Okay, so this assumes that we already know how to find the solution. Now, the next thing that I was asked to do is to find the particular solution that verifies the initial condition. So this is just, verifying. Now what I want is to find the particular solution. Okay, so to find the particular solution, what we'll do is we'll make sure that this equation over here is satisfied, right? So the idea here is really to make sure that this equation is satisfied. So I'm going to force that to be true. Okay, so I have that y of 1 will have to be equal to 4. Now, I already know, so we know that y is of the form, so has the form c, some constant times e to the 2x minus 2x minus 1. And all that I'm trying to figure out now is to find the value of c, right? So like I'm trying to figure out what the value of c over here is going to be. So if this is what I want to do, then that means I'm going to plug in 1 into the right-hand side. I'm going to evaluate y of 1 by plugging it into the right-hand side. So that means I get c times e to the 2 times 1, but e to the 2 times 1 is just e to the 2, minus 2 times 1, minus 1. Right? And that means that y of 1, so the function evaluated at 1, is going to be c times e to the 2 minus 3. Right? So this is by plugging into the function that we already know my y has to look like. But now I know that because of this equation over here, this has to be equal to 4. Right? So this comes from the equation that I already found for y. So I know that this has to be equal to 4. And so now what I'm going to do is to solve for the value of c. So now, by adding 3 on both sides, I have that c times e to the 2 is going to be equal to 7, right? So 3 plus 4, which means that the constant c is going to be equal to 7 over e squared, which is the same as to say 7 times e to the negative 2. Can I see a show of hands for those of you who understand this? Okay, great. So what that means is we already have the value of C now. So now I know that my constant C is actually just equal to 7e to the negative 2. And now if I want to give my final answer, then that has to be the actual solution to the initial value problem. So that means the solution that satisfies the differential equation and that satisfies, excuse me, the initial condition, which means that I'm going to have that y is equal to C, but C is equal to 7e to the minus 2. Times e to the 2x minus 2x minus 1. And here, just for the sake of not having to write e to the minus 2 times e to the 2x, because these two things have the same base, right? So for example, if I have x to the 1 times x to the 2, then I can just add the exponent. So here I can do the same. E to the minus 2 times e to the 2x is just going to be e to the minus 2 plus 2x, right? I can add their exponents as well. So that means that I'm going to get, this is going to be 7 times e to the minus 2 plus 2x minus 2x minus 1. And so my final answer is that the function y that satisfies the initial value problem is going to be 7 e to the 2x minus 2 minus 2x minus 1. This is my final answer. Do I have any questions about this, or is this okay for everyone? Who understood everything from A to Z? Okay, that's good. I have at least 13 out of the 60, so that means that's good. Maybe. All right, so I have that now. Let's backtrack on what I had over here. I was given
this manual.
Yeah. What's up?
See, bro, it looks like already.
Oh God,
yeah.
James?
Yeah. I
James?
think like 28 like max.
Okay, I'm gonna mute James. All right, so what I have over here is essentially that I was given the general solution, right? Then, so I was given the general solution. Then I verified that it was a general solution. And then once I had verified that this was a general solution by plugging it into the differential equation, I actually found the particular solution. Okay, so that means the solution that verifies the initial condition. So this is the steps that we followed in this type of problem, but of course, this all relies on the fact that we were given the general solution to begin. Now that's not always the case, and last time I finished with a first example on how to find the general solution for a given problem, but today we're going to be working on more examples in which we do this. So today we work on finding the general solution. Okay, this is the part that we're going to work on a little bit more. So for the following example, I'm going to ask you to work on the following. So we're going to find the general solution y prime is equal to x over y. Okay, and so I already started giving a couple of hints of how to start this type of problem. Today we're just going to work on this, so elaborate on this a little bit. Okay, so the first thing that I'm going to do with each of these type of problems, and this is what you should do with each of the problems in number 5, number 6, and number 7, is to write this with what we call Leibniz notation, which is just d something over d something else, right? So derivative of a given value with respect to another variable. So that means in this case, I'm going to have dy over dx. And this is going to be equal to x divided by y. Okay. Now, in this type of problem, what we have to do is, so our essential goal is to try to be able to integrate separately with respect to my two variables, right? So I have a variable y that depends on a variable x. I have the derivative of y as a function of x and y, but what I'm going to try to do is to integrate y and integrate x, each one on their own, right? So I'm going to try to separate both of those into independent problems and then to link them through an equation. Okay? So what that means is I should have all the terms that have y, I should have them on the same side, and all the terms that have x, I should have them on the same side, right? So I should have on one side of the equation everything in terms of x so that I can integrate with respect to x, and on the other side of the equation, everything that's in terms of y so that I can integrate with respect to y. So in this specific case, what that means for us is that we have to multiply by dx on this side and multiply by y on the left-hand side. Right? So we multiply by y both sides. On the right-hand side, it cancels the y, and on the left-hand side, it stays. And we multiply by dx on both sides. On the left-hand side, it cancels out, and on the right-hand side, it stays. So that means I'm going to have now, if I multiply by y, I'm going to get y dy over here. And on the right-hand side, I'm going to have x times dx, which means that I now have each part on their own, right? So here I have x and I have the dx, so everything is in terms of x. And on the left-hand side, I have y and I have dy. Everything is in terms of y. And at this point, I can actually integrate, right? So I can integrate left-hand side, I can integrate right-hand side. So that means I'm going to have that. If this equation is verified, then this equation is verified, right? All of my algebra here is right, which means that the integral of y times dy is equal to the integral of x times dx. Show of hands if you understand everything that I've been doing so far. All right, good. So what I have to do now is to integrate y with respect to y, integrate x with respect to x, and I'm considering them as independent problems, right? So I deal with my left-hand side, however I have to deal with my left-hand side, and I deal with my right-hand side, however I have to deal with my right-hand side. So then I'll have, on the left-hand side, this is y squared over 2 plus some constant. Okay, so I'm going to put this in another color. You're going to see y in a second. So I'm going to put this maybe in green, which I haven't used. So plus the first constant. And then on the right-hand side, I'm going to have x squared over 2. And I'm also going to have another constant, right? So maybe plus c2. So all that I've done now is integrate on both sides. I know how to integrate each of these functions. I should have no trouble. All right, so then the reason that I've put these in different colors is because really what we're trying to do is find a solution for y, right? So what that means is we're trying to integrate for both of these, but then we're trying to see what's going to happen with these functions. But by adding a constant on each of the sides, this is the same as if I had just added a constant on the right-hand side, where the constant on the right-hand side is just the constant on the left-hand side and the constant on the right-hand side combined, right? So I can rewrite this as y squared over 2 is equal to x squared over 2. And then plus C2 minus C1. But both my constant C2 and my constant C1 can take any values that I want, right? Like this could be equal to 0, 1, 2, 3 minus pi minus a billion, 3 billion, whatever I want. And so that means that this constant, whatever is added over here, is also arbitrary. So I could also consider this to be just a constant C. Right? So instead of always adding a constant on the left-hand side and on the right-hand side, what I can say is I can just, well, say that this is going to be y squared over 2, which is going to be equal to x squared over 2 plus c. So essentially at this point, once I'm integrating, I could just go straight to this type of problem over here and say, once I'm integrating, I'm only going to add the constant of integration to the right-hand side. You always have to add the constant of integration, but you don't have to do it on both sides because you'll always end up putting everything on the same side. So when you're integrating a function with respect to y on the left and with respect to x on the right, you're going to add the constant of integration just on one side. Okay? Do I have any questions about this, or is this okay? Okay. So that means that I have that y squared over 2 is equal to x squared over 2 plus 2 times c. What I'm going to finish doing now is to actually try to solve for the variable c, because for the variable y, because in this case it's not that difficult, right? So that means I'm going to get, if I multiply everything on the left-hand side by 2 and everything on the right-hand side by 2, I'm going to get that this is y squared is equal to 2 times x squared over 2, which is going to be just x squared, and then plus 2 times c. And that means that y is going to be equal to either plus or minus the square root of x squared plus 2 times c. Okay. So what I have now is I have found the general solution of my differential equation. I have found the general solution of my differential equation by simply just separating my problem into 2 independent problems, right? So I have the left-hand side and the right-hand side. Now, there's just one warning that I want to put over here. So one warning here is that I have 2 possibilities, right? So I have plus or minus square root of x squared plus 2c. I know that I have 2 hands that are raised, so I'll just address this, and then if you still have a question, I can answer it in a second. So one of the big things here is that I have that my solution has a plus or minus in front. Right? The reason that it has a plus or minus in front is that, well, when I have a square, the sign cancels out. So if I'm taking the root, I could be taking either the positive root or the negative root. How will I know if I should be looking at the positive root or the negative root? That's going to depend on the initial condition, right? So depending on whether my initial condition was positive or negative, I know that I will have to take either the positive root or the negative root, right? So I'm just going to write this down over here. Whether we choose the positive root or the negative root will depend on what the initial condition for this problem is. Okay, so whether we have plus or minus depends on what the initial condition is. Just going to write it a little bit smaller. Because that, so like so far the answer that we have is essentially an answer that tells me that my function could look like, my function could look, I don't know, like this, like that, or maybe it could look like this, or like that, right? So depending on whether you start with a positive or a negative initial condition, you're going to be able to determine which of the cases you're going to be in. Okay. Now I have Daniel and Dolan with questions.
How do you get the 2?
This 2? Can you show it to me? You have I think you can actually draw on my board.
Well, it's the 2 next to the y squared over
This
2.
one?
Yeah.
Okay, so what I'm trying to solve for in this case is y, right? So that means that at this point, let me just,
I have a similar question, basically.
oh, okay, good. So essentially over here, I have, based on this point, like the conclusion that I get from here is that y squared over 2 is equal to x squared over 2 plus a constant c, right? This is what this equation over here tells me, where I've just labeled my sum of these two constants as c. What I'm trying to solve for is y. Right? So I'm trying to get the number y over here, which means that I need to get rid of the 2 that I have at the denominator here, which is why I'm multiplying both sides by 2. I multiply this side by 2 and I can cancel the 2 that I had at the denominator, but then I also have to multiply the other side. So I'll distribute this to both of these terms. I'll get x squared, but then the constant that I have here, the 2 that I have here, is also going to multiply the constant.
Okay.
Technically, you could label this as this whole new constant, which is also completely reasonable. In this case, because it doesn't really make my expression look that much more complicated, I'm just going to keep it as 2c, but it doesn't really matter.
Okay.
Is that okay?
Yeah.
Okay, good. Shine, you also have your hand up.
Yeah, so when the 2 on the right-hand side multiplies onto x squared divided by 2 plus c, if c is an arbitrary value, then why doesn't it just become just another c? Like, what does it have to be 2c, or can we also
No, you could label this like this is going to be an arbitrary value, so you could also like label this as d, for example, and then you would have that your solution is going to be y is equal to plus or minus square root of x squared plus d. Right, so it's completely possible to just label it like that. There's no problem with this. Once we solve for c, you know, if you label it as d, you're gonna find, let's say, I don't know, 4. But then if we had labeled it as c in this case, then we would have found 2. So we're gonna find equivalent solutions. They're just going to be denoted in a slightly different way.
Okay.
All right, is that good for everyone? Hands up if you understand everything. Good. So I'm going to write another problem on the board. The new problem is also going to have an initial condition. So you're going to have to start it on your own. Hands up if you finished writing everything that's on the board. Okay, so I'll give you 1 more minute because I see a little bit more variation here. The next problem you're also going to have, actually I'm going to start writing it over here.
Manuel.
I'll write again. Sorry, there's a question?
Yeah.
Yeah, okay, what's up?
Well, I'm not sure to understand the graph. So.
Oh, okay, so like here I'm just saying like this would be the general solution. So this would be any type of function of the form square root of x squared plus 2c or minus square root of x squared plus 2c.
Oh, okay.
Right? And then depending on what the initial value actually would be, then you would know whether you're above the x-axis or below the x-axis. Right? So like if you have a value, for example, here, then that means that your solution is going to be positive root of x squared plus whatever the constant that you find is. But if you have maybe a value over here, then your solution is actually going to be of the form minus square root of x squared plus 2.
Okay.
Yeah. Okay, so I'm going to move to the next page and give you the next problem. So we have example. And for this one, you're going to have to solve a full initial value problem. Solve the initial value problem. Y prime is equal to x times y divided by x squared plus 1, where the initial condition is that y of 0 is equal to 5. Okay, so you know that this is the differential equation, and this is the initial condition. And just as before, the first thing you're going to do is to find the general solution, and then you're going to find the particular solution that also satisfies the initial condition. So if I'm going to put the y on the other side, then that means I'm going to have to divide both sides by y, right? Because here is being multiplied, so if I want to put it on the other side, then I'm going to have to divide. So that means here I'm going to have to divide it by y. Then I still have x over x squared plus 1 that has to stay on the right-hand side. So I'm going to have x over x squared plus 1 over x squared plus 1. And then I'm multiplying by the dx. Does everybody understand this? Can I see a show of hands for those of you who still don't understand what I did here? Still don't understand. Okay. All right, so it seems like it's all very easy when I do it on the board. That's great, not enough. So you have that this is dy over dx. I have now solved it in such a way that I have dy on the same side and as the y and x on the same side as the dx, which means that now I can actually start integrating both sides, right? So that means on the left-hand side, I'm going to integrate dy over y, which is the same as 1 over y times dy. And on the right-hand side, I'm going to integrate x over x squared plus 1 dx. Yeah. Who had gotten at least until this point? All right. So what I'm going to ask you to do now is to keep going with the problem. If you had already gotten to this point, that means you might be at the point where you're trying to solve for the initial condition as well. And for those of you who hadn't managed to start the problem, you can start integrating this piece as you think you need to integrate it. And I'll finish solving the problem in about 2 minutes. Okay, so you'll just get this head start and then I'll finish solving the problem. 2 minutes. What we're going to do here is to integrate 1 over y with respect to y. So that just means we have a function 1 over y, which is ln of absolute value of y. Right? So I think everyone should know this integral. We should be fairly confident with this. And what I said is don't add the constant of integration on the left-hand side because you can just add it on the right-hand side and it's equivalent. Right? Instead of having 2 constants of integration, you end up with just just one variable. So that means on the right-hand side, I still have to integrate x over x squared plus 1. Now, what technique of integration do you think I should use in order to integrate x over x squared plus 1?
Substitution?
U substitution. Yes, I have the 2 pieces given by separate people. So we can do U substitution in this case, which will tell me that if I choose U, in general, I try to use the denominator as my as the value of U, right? So in this case, I would have U is equal to x squared plus 1, which means that du would have to be equal to 2 times x times dx, right? And from here, I can get that, well, if I just have x dx to replace, which is the case in this situation, I will have to replace that by 1 over 2 times du. So I can replace 1 over 2 times du by x dx. Okay? And so on the right-hand side, I'm going to have the integral of 1 over 2 times 1 over u times du. Can I see a show of hands for those of you who understand this? Okay, that's good. So that means that I have 1 over 2 times ln of absolute value of u plus c. And I know that u is actually just equal to x squared plus 1, which means that I get 1 over 2 times ln of absolute value of x squared plus 1 plus c. And just as a reminder, this was ln of absolute value of y. Make sense? Okay, so at this point, I still would like to be able to solve for y, right? So I would like, if I can, and it's not always going to be the case, we know that sometimes we have to give implicit expressions for functions, but if I can solve for y, I would like to be able to do so, right? So the way that I'm going to do that in this case is I'm going to have to get rid of the ln of y, right? So that means I have logarithm being applied to y, and so if I want to get just y, I'm going to have to take the exponential of that logarithm, right? Because I know, here you have to remember this, that e to the ln of something is going to be equal to the something, right? So that's the idea over here. If I apply exponential to the logarithm, then that gives me the actual inside function of the logarithm, right? So for example, here, I will do e to the ln of y is going to be equal to e to the ln of this. To the ln of this, but before I get to do, before I put all of this on the logarithm, on the exponential, I'm going to say, okay, well, I know that logarithm of x squared plus 1, the whole thing divided by 2, is the same as if I had put this exponent over here, like this constant that's in front of the logarithm. I can just go and put it at the exponent of the function that's inside the logarithm. Who understands what I'm saying here? So remember, when I have a constant in front of the logarithm, I can put that back as the exponent of the thing that's inside the logarithm, right? So last semester when you were doing logarithmic differentiation, we were doing the opposite. So we were taking logarithm of something and the exponent and then bringing the exponent down. There's no reason why we shouldn't be able to put that exponent back up, right? So in this case, I'm going to have that. This is going to be e to the ln of x squared plus 1. And then I'm going to put the power of 1/2 over here right away. And I still have plus c. Right? So all that I did over here is put everything on the exponent of e and put the 1/2 of the exponent of that term as well. All right, so I'm going to keep going over here. So I have e to the ln of y is just equal to y, right? So the left-hand side I'm done with because I know e to the ln of something is equal to the something. Now, this actually looks like I'm going to be able to simplify it as well, right? So I have e to the ln of something is going to be equal to just the something. And so if I just had e to the ln of this, then I could get rid of the logarithm. The problem is that I still have the plus c over here. So what I'm going to do is to break this up because I know that a plus in an exponent is the same as a multiplication outside of it. So that means that over here, I'm going to get that y is equal to e to the ln of x squared plus 1 to the power of 1/2 times e to the power of c. Who understands this part? Okay, I see fewer hands. Who does not understand this part? All right, so still some hands. Okay, so is there anybody that doesn't understand how I went from here to there? No hands. Okay, so the problem is really from here to there, right? So what I'm doing over here is I'm saying, okay, this is e to the power of ln of x squared plus 1 to the power of 1/2. So that's to the power of a plus some other number, which in this case is c. And I know that e to the power of a plus c, I can break that into a product of e to the a times e to the c. And so that's equal to e to the a times e to the c. Right, so that's what I've done over here. My a is just this complicated expression, but then I've multiplied by e to the power of c. Right, so all I've done is break this into a product. Can I see a show of hands for those of you who still don't understand this? Aha, okay, that's good. So essentially, I'm just doing this operation, but with a more complicated expression in terms of a, right? So we know how to do it with constants. We also need to be able to do it with functions. It's just that in this case, I really want to separate these two so that now I can cancel the e and the logarithm over here, right? So the exponential and the logarithm, I can now cancel them out, and I get that y is actually equal to e to the c times logarithm of x squared plus 1 to the power of 1/2, which is x squared plus 1 to the power of 1/2. Okay? And then here again, we have that e to the power of c. C over here is just an arbitrary constant, which means that e to the power of c can take any possible value. Okay? And so that means over here, I'm just going to denote that as some other number d. There's no reason why I shouldn't be able to. E to the c is just going to be some other number. We don't know what that number is, so I'm just going to denote it by another letter. And then I'm going to write the power of 1/2 as a square root, just because sometimes it's easier to understand things like that. And so that means that y is equal to some constant, d, times square root of x squared plus 1. Can I see a show of hands for those of you who did understand this? That's very good. Okay, so when you are, okay, so we're not done yet. We have just found the general solution because we still have to find the particular solution that satisfies our initial condition. But let me just break over here for a second and kind of just make the point that over here, this is really the only way in which you could have separated the variables, right? And the reason that this is the only way in which you could have separated them is that when you're solving for dy in terms of dx, you need to make sure that you divide by the y. That's going to bring it to the left-hand side, and then that you multiply by the dx. If you are confused about how to separate the variables over here, make sure that whenever you're multiplying or dividing by something, you put brackets around the thing that you're dividing by, right? So that will help you see what you can and cannot divide by. Because, for example, in this case, here you don't have to write this. It's just a proof of concept. So it's just pay attention, then it will be okay. So in this case, if you were to just like multiply by x squared plus 1 on this side. So if you had, let's say, I don't know, x squared plus 1 dy is equal to x times y times dx, then you would end up dividing by y over here, which is no problem. But if you were to divide by something on both sides, it would have to be something that is a factor of the left-hand side. And in order to realize what is a factor, you need to make sure that all of your brackets are in place, right? Because if you try to divide here by x squared, it won't make any sense because you will be dividing by x squared, but then the plus 1 is kind of just staying on its own, right? You have to divide by something that is a factor. And if there's a plus in between the two terms, then it is not a factor, it is a term. It is something that is being added, not something that is being multiplied. Does everyone understand this? Yeah, so like even if you had done this before, you'll realize, okay, eventually I do have to divide by y. But then on the right-hand side, I have x times dx. And if I want to divide by the term that's being multiplied over here, I have to divide by the whole factor, which in this case is not just x squared, it's x squared plus 1. So I need to divide by x squared plus 1 as well. Does everybody understand that? Do I have any questions about this? All right, so just make sure that you're careful with the way that you are separating your variables, because there's always going to be just one way of separating variables. There might be like equivalent ways, but you have to make sure that you're always dividing or multiplying by whole factors and not by just pieces. You can't just, the same as dividing by two things that have a plus in between at the denominator or something. It doesn't work. Yeah. All right, so this is just like something to keep in mind. But now we need to finish a problem that we started. So we're gonna have and here. So the second part is to find the particular solution. The particular solution. And so that means we have y of 0 is equal to 5. But I also know that y has to be of this form. So that means y of 0 is equal to d times square root of 0 squared plus 1, which is d times square root of 1, which is just 1. And so this tells me that y of 0 is equal to 5. Y of 0 is also equal to d. So that means that d has to be equal to 5, right? And my particular solution of the initial value problem will actually be y, or y of x, you can also write it like this, is equal to 5 times square root of x squared plus 1. And this is our final solution. Do I have any questions? Show of hands for those of you who understood everything that I did for this problem. Okay, seems okay. I will give the last problem for the day. I'll ask you to start it up. If you have the question, if you have the answer by 5 minutes from now, that will be great. You can let me know. If you have any questions, you can ask me as well through the chat. And then I'll start Thursday by solving this type of problem, and then we'll do solutions to like our real life problems, which are problems from like the first problem of this problem set. Okay, so by Thursday, put this on your agenda, you need to finish all problems up to problem number 5. Okay, solutions are going to be posted probably later today. I still have just a couple of problems in problem number 7 to solve, and then after that, you should be okay. So by Thursday, everything up until number 5. For the remainder of today, we're going to do the following. Example, which is solve the following IBP. Solve y e to the x plus, plus y squared minus 1 times y prime is equal to 0. And y of 0 is equal to 1. Okay, and I'm going to put a big warning over here, because for this problem, you're going to find an implicit definition for y, right? So that means that you won't be able to solve for it. So can't solve for y. Okay, so you can start on this, and then I'll start with the solution for this on Thursday. And to any problems that you have, please do as much as you possibly can for Thursday. It's really going to be a lot easier to handle on Thursday if you have this before, because we're going to start working on the applications that we've seen before, and those are really not obvious to solve. So the more you have done by then, the easier it's going to be.